Today we are looking at structure 1.2, the atom, and if you haven't already done this, pause the video and download today's PDF. The link is in the description. So this is so you can make your own notes as we go through today's topic, which includes what are the subatomic particles and where are they found, masses and charges of the subatomic particles, Nuclide notation, isotopes, and mass spectra. So, what are the subatomic particles and where are they found? So, protons and neutrons found in the nucleus, and they are also called nucleons, and electrons are found in energy levels which are made up of orbitals. So atoms are the smallest bits of matter that can take part in a chemical reaction. They are made up of three subatomic particles. We've got the protons and the neutrons making up all of the mass, and electrons making up all of the volume. We will find out more about how electrons like to spend their time in the next video, but to give us some idea of what's going on in the atom, we're going to have to use the full power of our imaginations. So this is only going to work if you close your eyes. So go on, close your eyes. If you don't do it, you're not going to get a 7. So hopefully you're all sat there now with your eyes closed. So imagine you are the size of a small mouse and you are standing in the biggest room or the biggest stadium you've ever been in. You are now a nucleus. Fun, isn't it, being a mouse-sized nucleus? So look around at everything you can see. Everything that you see basically has no mass, but it has volume. So this is the volume of an atom. So all of the mass of everything that you can see, that mass is inside you. You as a little mouse-sized human. So try lifting your arm. It's not easy, is it? And that's because it is dense. You are incredibly dense. You are right now more dense than you will ever realize. Okay, so that is you as the nucleus. Now you are going to become an electron. So you are not moving around in nice little circles as a lot of the diagram suggests. You are everywhere, all at once, all at the same time. So if you just look at the building that you're in, so the walls of that building or the walls of the stadium, they're always there. But as an electron, you are everywhere, but there's only one of you. So as an electron, you are everywhere. Yeah, the only difference is you basically have no mass. So no easy task being an electron, but there you go. Okay, so now open your eyes nice and slowly and come back to the world where everything makes sense. So let's talk through these diagrams that we've got here. So, yeah, so here is the nucleus, made up of the nucleons with the protons and the neutrons. And we have all of our positive, so all of our positive protons, and yeah, the neutral neutrons. And the reason that all of the positive things can stay in one place is due to the strong nuclear force. So this is stronger than the electrostatic repulsion that would be between the two positive or the positive protons. So it's the strong nuclear force that keeps everything together. And then, yeah, so here we've got the electrons in their shells, but as we've said, it doesn't look like this. So what we've got over here is like a better representation of the atom. So this is the nucleus in the middle. So remember, you are a mouse-sized nucleus, and you are incredibly dense, the heaviest you've ever been. And yeah, the electrons are occupying the whole space, but they're very small. They've basically got no mass, but they are everywhere, all at once. So this is, yeah, a very tricky thing, but we're going to find out more about this, in the next video. Okay, so now on to the masses and charges of the subatomic particles. So here we go. So this table you will be very familiar with if you've done chemistry before, which I'm sure most of you have. So yeah, so anything with a charge has an electric field, and electric fields interact with each other. So like charges repel, so as we saw with the nucleus, like charges repel, and yet opposite charges attract, as we will see later in action in the mass with the mass spectrum. So you might get asked to do stuff with the actual masses, so with the actual masses and the actual charges. So yeah, if that does happen, head to the data booklet where you will find all the data you need. So namely the real life masses of a proton in kilograms and the charge of thing in coulombs. Yeah, so these are just relative charges at the moment, so just a +1, -1, and then yeah, relative masses which is fine for pretty much everything you need to do in chemistry, but sometimes you might need to actually look at using the real data values. And then as we can see, the mass of an electron is almost nothing. Okay, so on to Nuclide notation. So every element lives in a box. So it lives in a box in the periodic table, and if it's not in a box, then it is not an element. So each element has its own unique proton number, which has the symbol Z, and this is just how I do my Zs. Sometimes you need to get over that. And each element has its own unique chemical symbol. And then so for elements with 2 letters, the second letter is always lowercase. So like copper, it's always like a lowercase c. Mg, lowercase g. So back to the proton number. So this is one of the things that provides order in the periodic table. So as you go across the period, going across the period, the proton number goes up by 1. Then the final number that we've got here is the mass number. So this is the mass number. So the mass number is the number of protons and neutrons added together. So from the mass number and the proton number, we can work out the neutron number. So elements can have different masses, giving us isotopes, which is what is going to be coming up next. And you can also have different elements with the same mass number, and this is not a problem, as we're going to look at in a second. So argon has a proton number of 18, potassium has 19 protons, and calcium has 20 protons, but all of them have the mass of 40. So the key thing is that each element has its own unique proton number and unique symbol. Then the atomic number also gives you the number of electrons in a neutral atom. So what we're going to do now is you can do these things called pen calculations, proton, electron, neutron calculations, to figure everything out. And you can also use them to help you understand why ions form. So we're going to be using argon, potassium and calcium as an example. So let's start off with argon. Then we're going to write pen, P-E-N. So we do the notation as well for it, so it would be 18 and then 40. So this is what argon would look like on the periodic table. So we know that it has 18 positive protons. It's a neutral atom, so it has 18 negative, 18 negative electrons. And then 40 minus 18 is going to give us 22 neutrons. Nice and easy. So let's go on to potassium. So potassium has the symbol K and always has the number of protons as 19. So let's just do our pen calculation nice and quickly. So 19 positive protons, 19 negative electrons, and then in this case 21 neutral neutrons. And then finally we will go for finally we'll go for calcium. So calcium, P-E-N. So 20 positive protons, 20 negative electrons, and 20 neutral neutrons. So now let's see how we can do this with an ion. So calcium, so calcium, if we have the calcium ion, so calcium likes to form a 2+ ion. So its proton number is going to stay exactly the same, so that's 20. This time, so we've lost 2 electrons, it's going to have 18 negative electrons. We don't really need to worry about the neutrons. So overall the charge is 20, so we've got plus 20 minus 18, so this is giving us a +2 charge. So this is how ions are formed. It's when there is a different number of electrons. So number of electrons can change, number of protons can't. So this is really important, especially when we look at how compounds are formed. Okay, so now on to isotopes. So isotopes are atoms which have the same number of protons but a different number of neutrons. And then radioisotopes are unstable atoms that emit radiation from the nucleus. We'll look at that afterwards. So here we have an example here. So most elements are slightly different. What makes them slightly different is the number of neutrons they have. What makes an element is its proton number, which is the same as the electron number, and it is the protons and the electrons that are responsible for most of the chemistry. So what the neutrons do, so the neutrons help provide the strong nuclear force, which keeps the nucleus nice and stable. But what they also do, and this is what we're going to be talking about next, is that they can slightly change the physical properties of that specific isotope. So these three isotopes here, are going to have slightly different physical properties. So so things like melting and boiling point. So let's have a look at how this works by using a model. So we can imagine an element as a herd animal. We've done it before in our last video. So pick your favorite herd animal right now. If you're struggling to think of one, you can choose from either a goat, a bison, deer, zebra maybe, could be a camel, and even a donkey. Okay, so you should be picturing your herd animal, your big herd animal, and of course you've gone for the llama. So you know that it's a llama because that's what they look like. But if you look a little bit closer, some will be bigger and some smaller. For the bigger llamas, they might not be able to move so fast. So with the elements, this would be the diffusion rate. So this would be the diffusion rate. So it could be, so diffusion is one of the things that affected. So so heavier isotopes diffuse slower. Okay, now sticking with our big llama, so the bigger llamas might not be able to jump as high. So with the elements, this would be, melting point and boiling point. So heavier isotopes would have a higher melting and boiling point. And with those bigger llamas, they are going to be more dense. And with the elements, the same is true. So make sure we spell dense properly. So if the isotope has a bigger mass number, the nucleus, and therefore the atom, will be more dense. So usually, all the different isotopes of one element are mixed together, so the physical properties will be the same. It's only when you isolate the isotopes will you see the difference. So let's go back to hydrogen over here. So we can use hydrogen here as an example. So because this is our lightest isotope of hydrogen, its melting point, boiling point is going to be lower compared to this type of hydrogen. This one's going to be able to diffuse quicker, going to diffuse at a quicker rate, and this one is going to have a slightly lower density compared to this hydrogen over here. So there we go. So those are how we've got the differences between the three. And we're going to have even more difference between these three because it is quite a lot bigger. So this one is 3 times bigger than this one. So the differences won't be as big if we're looking at different compounds and elements. Okay, so now on to radioactive isotopes. So with some elements, the number of neutrons just isn't quite right. So this means the nucleus is unstable and undergoes radioactive decay to try to get rid of some of that energy, and as a result it undergoes a change. So it changes the atom that it is. So it's hard to imagine how this would happen with our herd animals, but it might. So you might have an unstable llama with too much energy and no idea what to do with it, until one day it emits some radiation, basically lots of energy, and becomes an antelope, and they all live happily ever after. Probably. So this is what happens with radioactive isotopes. The nucleus has too much energy, so the only way to get rid of it is via radioactive decay. And when you look at things on an atomic scale, energy and mass are almost the same thing. So this is Einstein. This is where Einstein's famous equation came from, so E equals mc squared. Right, so again, more silly analogies. As always, I would love to hear what you think the strengths and the weaknesses of this model that I have used today. So drop your thoughts in the comments below. Right, so back to today. So as you might have noticed on your IB standard issue periodic table, most of the elements do not have a whole mass number. And yet this is because of the isotopes, and yet the isotopes are all mixed together. So the mass of the elements is worked out by taking the average mass from the different isotopes. So here is how the calculation is done. So here we go. So we're going to be using iron as an example. So most of iron is iron 56. We've got a bit of iron 54 and iron 57. So those numbers there, so that's the mass number. And we have their relative abundance as well. So that's going to equal to a total of 100%. So you put the numbers into our equation. So we've got 54, and that has an abundance of 5.95. Then we have isotope 56, which has an abundance of 91.88. And isotope 57, so iron 57, has a relative abundance of 2.17. So you put all of the numbers in, and you then get your answer. So so nice and easy. So I will do an example of this in a second once we figured out where these numbers come from. So these numbers are coming from the mass spectra machine. Okay, and here it is. So how does this lovely machine work? So strictly speaking, you only need to know this if you are an HL student. However, this is only a short introduction. Another video for another time will be going into more detail. But this is a good overview for all to enjoy. So today we're going to be using some chlorine. So this goes into the inlet. So so chlorine will be going into our inlet. Then you need to vaporize your sample. You need to give it lots of energy, lots of kinetic energy. So heating it up. So this will turn it into a gas if it's not already a gas. But regardless of the element, it's going to give it lots and lots of energy. So first thing we're going to be doing is vaporizing it. Then the second step is to ionize it using an electron beam. So you're hitting it with high energy electrons to force it to become a positive ion. So this is key, as it needs to have a positive charge for the rest of these things to happen. So now we've got a positive ion. So because it's got a positive ion, it is now attracted to the negative plate. So it's accelerated using these negative plates. It's accelerated nice and quickly using these negative plates. And then, as it has a charge, so anything with a charge has an electric field. And this electric field interacts with this magnetic field. So we've got this magnetic field here. And this magnetic field is causing deflection. So without the magnetic field, everything will just keep going in a straight line. The magnetic field is causing deflection. So they're bending round a corner. And it causes the ions to move around the bend, and then it's hitting our detector. So the ions hit the detector in different places depending on their mass. So different masses deflect differently. And then finally, our detector is connected to a fancy computer, which turns what is detected, what is felt, into a lovely mass spectrum. And then you get to print it out, and then you get to look at some lovely lines. So this is one of the uses of mass spectrometers, to find out the isotopes present in an element. But they can also be used to find out the structure of molecules, and that's something that we'll look at in a future HL only video. Okay, so as we said, our sample today was chlorine, so chlorine's gone in. The fancy computer has done its work, and then this is what you get as a result. Happy days. So we can see that we've only got 2 isotopes for chlorine, so 2 peaks, 2 isotopes. We've got their relative abundance. So the lighter isotope, so we've got here, is at 75%, and then the slightly heavier isotope is at 25%. So let's just go through this graph quickly. So this axis here is giving us the mass, so the mass number. So in this case, it's just going to be the atomic mass, and then this axis over here is relative abundance. So using the same equation as before, we can put our numbers in. So we have 35 times 75, and then when we add that to 37 times 25, all of that divided over 100, that's going to give us 35.5, and yet that is the atomic mass, or the average mass, for chlorine. So yeah, just quickly going through this again. So we have 75, 25, so those would be the mass numbers here, and then these are the numbers here, and then yeah, getting an answer of 35.5. Happy days. Okay, so there we are, atomic structure done. Thank you as always for watching, and if you want some more new IB chemistry content, please do like and subscribe. And if you are desperate for a specific video on a specific topic, then please do let me know in the comments and I will see what I can do. Then final thing, if you are after more chemistry help in the form of tutoring, and from me specifically, we can speak in real life over an interactive whiteboard, then check out my website, link is in the description. And yeah, thank you again for watching, catch you in the next one, ciao.